There is a number that keeps planetary scientists awake at night. Not a large number, not a dramatic one, just a ratio, the fraction of planets that begin with the right conditions for life and actually sustain those conditions long enough for anything interesting to happen. We do not know this number. We have exactly one data point: Earth. One planet where the conditions held, where liquid water persisted, where complex chemistry had enough time to produce something that could eventually look up and ask questions about the universe. One planet where the whole chain of events worked. What we do know, with increasing precision from increasingly good data, is how many ways it can fail to work. How many planets begin with promising conditions and then lose them. How many worlds start warm and wet and end frozen or burned or stripped bare. How many times the universe has, by every indication, given life a chance and then taken it away. The answer to that question is uncomfortable. Not because it is uncertain, we have made our peace with uncertainty, but because the more we understand about how planets die, the more recognizable the warning signs become. And some of those warning signs are not only recognizable, some of them are measurable. Some of them are measurable here. Tonight, we are going to look at the evidence, at the specific data from specific missions, from specific observations of specific worlds, at the mechanisms by which planets lose the conditions for life, and the timescales on which those losses occur. We are going to look at what the solar system tells us about planetary death, and what that implies for Earth. Not in the vague sense of eventual stellar death billions of years from now, in the specific sense of the mechanisms that operate on timescales that are neither geological nor astronomical, but something in between. Timescales that are measurable in millions of years rather than billions, in thousands rather than millions. And we are going to be honest about what we find. If you are here because the night is long and you want something to sink into, stay. This is one of those subjects where the further you follow the evidence, the more the comfortable assumptions dissolve and the more the actual picture emerges. The actual picture is not hopeless, but it is not reassuring either. It is honest. And honest on a question this important is the best thing it can be. Let us begin with Mars. Mars is not a dead planet in the way that the Moon is dead, geologically inert, geologically ancient, wearing its craters like a record of impacts that occurred before most of the solar system's current configuration existed. Mars has weather. It has seasons. It has a thin atmosphere that redistributes dust across global scales. It has polar ice caps that grow and shrink with the Martian year. By certain definitions, Mars is alive, dynamically active in ways that distinguish it from the truly inert surfaces of airless bodies. But Mars is dead in the way that matters most. It has been dead in that way for approximately 3.5 billion years. We know this because we can read the record. Mars's surface is an archive of its own history in a way that Earth's surface is not, because Mars lacks the plate tectonics that on Earth continuously recycles crustal material, erasing old records and replacing them with new ones. The surface of Mars is old. Ancient terrains in the southern highlands date to more than 4 billion years ago, terrain that has been sitting, accumulating craters since before complex life existed on Earth. And embedded in that ancient terrain is the evidence of a world that was once completely different. River valleys. Not the subtle channels that might result from seasonal frost sublimation or CO2 deposition. Real river valleys, dendritic drainage networks that branch and merge in the patterns that water makes when it flows across a landscape over long periods. Valley networks covering thousands of kilometers of ancient southern highland terrain, preserving the record of a time when liquid water moved across the Martian surface in quantities large enough to carve significant topographic features. lake basins, craters that filled with water, accumulated sediments, and in some cases had outflow channels where the lake overflowed its rim. Gale Crater, where the Curiosity rover has been exploring since 2012, was once a lake, possibly for millions of years. The sedimentary record that Curiosity has been reading layer by layer is the record of that lake's history. The chemistry of the water, the character of the sediments, the environmental conditions that changed over time. Delta deposits. Where rivers entered standing bodies of water, they slowed and dropped their sediment load in the fan-shaped formations that geologists call deltas. Jezero Crater, the landing site for the Perseverance rover, contains one of the best preserved ancient river deltas in the solar system. The delta in Jezero records a time when a river flowed into a lake, depositing sediments that now, after 3.5 billion years of preservation, are being sampled by a rover looking for signs of past life. The chemistry of ancient Mars is written in its minerals. Phyllosilicates, clay minerals that form in the presence of liquid water, are widespread in the ancient terrain. Carbonates, minerals that precipitate from water with specific chemical properties, are present. Sulfates that record the chemistry of water that moved through volcanic rock. The mineralogy of Mars is a chemical diary of a world that once had liquid water interacting with rock over long periods, in ways that produce specific mineral assemblages. All of this is consistent with one picture. Early Mars, for perhaps the first 500 million years of its existence, had liquid water at its surface. Not necessarily a global ocean, not necessarily continuously, not necessarily everywhere, but liquid water that flowed and ponded and interacted with rock and chemistry over timescales long enough to carve valleys and fill craters, and produce the mineral signatures we now read from orbit and from the surface. And then it ended. Approximately 3.5 to 3.8 billion years ago, the conditions that sustained liquid water on Mars disappeared. The surface dried, the valleys stopped flowing, the lakes evaporated or froze. The climate shifted from one that permitted liquid water, however intermittently, however seasonally, to one that has maintained an average surface temperature of approximately -60 degrees Celsius ever since. The water did not disappear entirely. It retreated to the poles, to the subsurface, to ice deposits buried under regolith, to the thin traces of water vapor in the atmosphere. Mars today still has water. It just has it in forms that are unavailable to chemistry in the way that liquid surface water is available. It has it frozen and buried and sequestered. What caused the transition? The answer is not simple and is still being actively researched, but the broad picture is understood. Mars lost its magnetic field, and losing its magnetic field, it lost its atmosphere. And losing its atmosphere, it lost the conditions that could sustain liquid surface water. Let us talk about why the magnetic field matters. Because this mechanism is not specific to Mars, and because understanding it is essential for understanding what it means for a planet to hold on to the conditions for life. Earth has a strong global magnetic field, generated by convection of liquid iron in the outer core, driven by heat flowing outward from the deep interior. This field extends far into space, creating the magnetosphere, a vast region of space dominated by Earth's magnetic field rather than by the solar wind. The solar wind is not a gentle thing. It is a continuous stream of charged particles, protons and electrons, flowing outward from the Sun at several hundred kilometers per second. At Earth's position, the solar wind carries sufficient energy to strip gas from the upper atmosphere. Without the magnetosphere deflecting this stream around the planet, the solar wind would continuously erode the atmosphere, ionizing atmospheric particles at the top of the atmosphere and accelerating them away from the planet with the solar wind. Earth's magnetosphere prevents this. It acts as a shield, deflecting the solar wind around the planet and protecting the atmosphere from this continuous, erosive process. The solar wind does affect Earth's magnetosphere. The interactions produce the aurora, the Van Allen belts, the complex space weather that affects satellites and power grids. But the net effect on the atmosphere is protection. Earth has kept its atmosphere because it has kept its magnetic field. Mars had a magnetic field once. We know this because ancient magnetized rocks on the Martian surface preserve the remnant magnetism of a time when the field existed, the same way that magnetized rocks on Earth's ocean floors preserve the history of Earth's magnetic field reversals. The ancient Martian crust is magnetized in patterns consistent with a global magnetic field that operated early in Mars's history. Then, approximately 4 billion years ago, Mars's magnetic field died. The exact cause is debated. Candidates include a giant impact that disrupted core convection, or the simpler cooling of a smaller planet that lost its internal heat faster than Earth, or some combination of factors. But the outcome is clear: the field stopped. And without the field, the solar wind had direct access to the Martian atmosphere. The erosion was not instantaneous, but it was relentless. Over hundreds of millions of years, the solar wind stripped hydrogen from water molecules in the upper atmosphere, allowing hydrogen to escape to space and leaving oxygen behind. It eroded the heavier atmospheric gases more slowly. The process that MAVEN, NASA's Mars Atmosphere and Volatile Evolution mission, has been directly measuring since 2014, stripping approximately 100 grams of atmosphere from Mars every second, even today, has been operating for billions of years. The result is the atmosphere Mars has now, a thin wisp of mostly carbon dioxide at about 1% of Earth's surface pressure, insufficient to maintain liquid water, insufficient to buffer temperature swings between day and night, insufficient to protect the surface from ultraviolet radiation. An atmosphere that is a remnant, a shadow of what Mars once had, eroded away by the same stellar wind that Earth's magnetic field continues to deflect. Mars died slowly over hundreds of millions of years by losing its magnetic field, and then losing its atmosphere, and then losing its liquid water. The process was not dramatic from any individual perspective within that time frame. It was gradual, the climate shifting, the rivers flowing less reliably, the lakes shrinking, the surface drying, the atmosphere thinning, over timescales so long that even geological records struggle to preserve the detail. But it happened. A world that had liquid water and warm chemistry and the conditions that, by our best understanding, are required for life, lost those conditions. And it has kept them lost for 3.5 billion years. Now let us talk about Venus. If Mars is the cold, dead world, the world that lost its warmth and its water and its atmospheric protection, Venus is the other story. The story of what happens when a world does not lose heat, but gains it. The story of the runaway. Venus is almost exactly Earth's twin in terms of size and mass. It is 95% of Earth's diameter and approximately 81% of Earth's mass. It orbits at 72% of Earth's distance from the Sun. Closer, certainly, but not dramatically so. By the basic parameters that determine planetary character, Venus should be something like Earth's neighbour in the deeper sense, a world where conditions are at least plausibly similar. Instead, it is an inferno. Surface temperature approximately 465 degrees Celsius, hot enough to melt lead, hot enough to soften zinc, hotter than the surface of Mercury, despite Mercury being far closer to the Sun. Atmospheric pressure at the surface approximately 92 times Earth's, the pressure you would experience about a kilometre underwater in Earth's oceans. An atmosphere composed almost entirely of carbon dioxide, with clouds of sulfuric acid at altitudes of 45 to 70 kilometres that reflect so much sunlight that Venus is the brightest object in Earth's sky after the Sun and Moon. Venus is the most hostile surface environment in the solar system for human beings. The Soviet Venera probes, the only spacecraft to ever successfully land on and return data from Venus's surface, survived for between 23 minutes and 2 hours before being destroyed by the heat and pressure. The longest surviving Venera returned data for 110 minutes. After that, silence. What happened to Venus? The short answer is we do not know completely. The long answer involves a runaway greenhouse effect of some kind, but the specific trigger, the specific timing, and the specific dynamics are not fully understood. This uncertainty is itself important, and we will return to it. What we do know is that Venus was not always like this. Geological evidence, the pattern of volcanic features, the lack of plate tectonics in the Earth-like sense, the specific resurfacing events recorded in crater densities, suggests that Venus underwent a dramatic global resurfacing event approximately 300 to 700 million years ago, in which the entire surface was remade by volcanic activity on a scale that has no precedent on Earth. Before that event, the surface record is largely erased. We cannot read what Venus was like more than 700 million years ago from its current surface. But climate models and the general understanding of planetary habitability suggest that early Venus may have been substantially different. Computer models published in 2016 and subsequently refined suggest that early Venus, rotating more slowly than it does today, with different solar luminosity before whatever event triggered the current climate state, may have had liquid water at its surface for as much as 2 to 3 billion years. If those models are correct, Venus may have been habitable, genuinely, substantively habitable, for longer than multicellular life has existed on Earth. And then something changed. The models suggest that increasing solar luminosity over billions of years, the Sun gets approximately 10% brighter per billion years as it ages on the main sequence, eventually pushed Venus past a threshold. The oceans began to evaporate. Water vapor, which is itself a greenhouse gas, amplified the warming. More warming evaporated more water, which amplified the warming further. A feedback loop, the runaway greenhouse effect, took hold. The oceans boiled away. The water vapor in the atmosphere was eventually dissociated by ultraviolet radiation, with hydrogen escaping to space and oxygen reacting with rocks. What remained was CO2, volcanic outgassing, and heat. The runaway greenhouse on Venus may have been triggered by something as gradual as the slow brightening of the Sun. Not an impact, not a cataclysm, just the steady increase in stellar output that characterizes every main sequence star as it ages, eventually pushing a planet past the critical threshold at which positive feedbacks take hold and the climate cannot be stabilized. This is significant. It means the transition from habitable to uninhabitable, if Venus was indeed habitable, did not require an extraordinary event. It required only the normal aging of the Sun and the presence of a planet close enough to the threshold that the brightening eventually crossed it. Now let us hold these two stories, Mars and Venus, alongside each other and think about what they reveal. Mars lost its magnetic field, lost its atmosphere, lost its liquid water. Gradually, over hundreds of millions of years, by a mechanism that ultimately traces to the planet's interior cooling faster than Earth's, it being smaller, having less internal heat to sustain the convection that generates a magnetic field. Venus may have lost its oceans and its habitability to a runaway greenhouse triggered by nothing more dramatic than the Sun getting slightly brighter over billions of years, crossing a threshold that turned a positive climate feedback from a stabilizing system into a destabilizing one. Two different mechanisms, two different timescales, two different failure modes. But the same outcome: worlds that may have been habitable, that are now profoundly hostile to the chemistry of life as we understand it. And Earth sits between them. Literally, in orbital terms, Earth is between Venus and Mars, and in the space of planetary possibilities, Earth sits in what appears to be a narrow range of conditions that sustains habitability, a range that Venus may have once occupied and left, that Mars may have once occupied and left, and that Earth currently occupies. The question that the comparison demands, the question that we have to be honest about, is how stable Earth's position in that range actually is. Whether the conditions that sustain Earth's habitability are self-reinforcing or fragile. Whether the planet we are on is the resilient exception or the temporarily lucky case. Let us talk about what sustains Earth's habitability. Specifically, the mechanisms that have kept Earth in the habitable range for approximately 4 billion years, while Venus and Mars both moved out of it. The most important mechanism is one that most people have never heard of: the carbonate-silicate cycle. It is a planetary thermostat, and understanding it is essential for understanding why Earth has remained habitable as long as it has, and what the limits of that stability are. The basic principle is this: carbon dioxide in the atmosphere acts as a greenhouse gas. It traps heat and warms the planet. But CO2 also reacts with rainwater to form a weak acid, carbonic acid, which reacts with silicate rocks in a process called chemical weathering. This weathering removes CO2 from the atmosphere and eventually deposits it as calcium carbonate, limestone, in ocean sediments. So there is a continuous sink for atmospheric CO2, chemical weathering. If left to run without any resupply, this process would gradually remove CO2 from the atmosphere, cooling the planet. The resupply comes from volcanoes. Plate tectonics continuously recycles oceanic crust, pushing it under continental margins where it descends into the mantle, heats up, and eventually returns its CO2 to the atmosphere through volcanic outgassing. The limestone deposited in ocean sediments rides the tectonic conveyor belt into subduction zones, is heated, and releases its CO2 back to the atmosphere. The thermostat operates because the rate of chemical weathering is temperature sensitive. When the planet warms, more CO2, higher temperatures, the weathering rate increases, removing more CO2 from the atmosphere and cooling the planet. When the planet cools, less CO2, lower temperatures, the weathering rate decreases, allowing volcanic CO2 to accumulate and warming the planet. The system is self-correcting. It acts as a planetary thermostat, maintaining conditions within a range compatible with liquid water over geological timescales. This thermostat is one of the primary reasons Earth has remained habitable for 4 billion years through the significant brightening of the Sun. As the Sun has gotten brighter, the thermostat has responded, drawing down atmospheric CO2 to reduce the greenhouse effect and maintain roughly stable surface temperatures. The evidence is in the geological record. Early Earth had dramatically higher CO2 concentrations than today, providing more greenhouse warming to compensate for the fainter young Sun. CO2 concentrations have declined over geological time as the Sun has brightened, maintaining surface temperatures within the range compatible with liquid water. Mars lost this thermostat when it lost its plate tectonics, or never had it in the same form. Without active plate tectonics, there is no volcanic resupply of CO2 at the rate required to maintain the balance, and the weathering sink continues to remove CO2 without resupply. Venus may have lost it when its oceans evaporated, because liquid water is essential for chemical weathering. Without oceans, the weathering sink stops. CO2 from volcanic outgassing accumulates in the atmosphere without removal. The greenhouse effect intensifies. The thermostat breaks. Earth's thermostat is functioning, but it has limits, and those limits are becoming relevant on timescales that are shorter than the geological timescale, shorter in some cases than the timescale of human civilization. This is where the conversation becomes uncomfortable. The carbonate-silicate cycle operates over millions of years. It is a slow thermostat, effective on geological timescales, unable to respond to rapid changes. When carbon dioxide is added to the atmosphere faster than the weathering cycle can remove it, much faster, the thermostat cannot compensate. The warming happens faster than the feedback can correct. Human industrial activity currently adds approximately 37 billion metric tons of CO2 to the atmosphere annually. The natural weathering cycle, under pre-industrial conditions, removed CO2 from the atmosphere at a rate of approximately 0.3 billion metric tons per year, more than 100 times slower than the current rate of addition. The thermostat is not broken, but it is being overwhelmed, asked to respond to a perturbation on a timescale orders of magnitude faster than it evolved to handle. This does not mean Earth is becoming Venus. The physics of that transition are different and more severe. The runaway greenhouse that may have transformed Venus required the complete loss of the oceans, which requires sustained warming of a magnitude and duration that goes beyond current trajectories by a substantial margin. But it does mean that Earth's thermostat, the mechanism that has sustained habitability for 4 billion years, is being tested in a way it has not been tested in the recent geological past. And the geological record of past rapid carbon perturbations, the Paleocene-Eocene thermal maximum, the end Permian extinction event, others, is a record of significant disruption, even in cases where the perturbation was less severe than what current trajectories imply. We will come back to this. But first, let us talk about something even longer term, about the ultimate fate of Earth's habitability and what the physics demands will happen regardless of what human civilization does. The sun is getting brighter. This is not a prediction. It is a physical consequence of the nuclear reactions that power every star on the main sequence. As hydrogen fuses to helium in the core composition changes, and the star adjusts its structure in ways that increase luminosity over time. The Sun today is approximately 30% brighter than it was when Earth formed 4.5 billion years ago. In approximately 1 billion years, it will be roughly 10% brighter than it is today. In approximately 5 billion years, it will expand into a red giant, engulfing the inner planets. The red giant phase is often cited as Earth's ultimate end. But the red giant phase is not when Earth becomes uninhabitable. It is when Earth is destroyed. The actual loss of habitability, the transition from a world where life is possible to a world where it is not, happens significantly earlier. The mechanism is the one we have just discussed, the carbonate-silicate thermostat. As the sun brightens, the thermostat responds by drawing down atmospheric CO2, reducing the greenhouse effect to compensate for the increased solar energy. This works and has worked for 4 billion years. But it has a limit. CO2 concentrations cannot go below zero, and the thermostat is approaching that limit. Current atmospheric CO2 concentrations, even elevated as they are by human industrial activity, are in geological terms relatively low. In the Cambrian period, 540 million years ago, CO2 concentrations were approximately 15 times higher than today. Over the subsequent 540 million years, as the sun brightened, the thermostat drew CO2 down to current levels. The trend is clear and the physical limit is visible. At some point in the next several hundred million years, estimates range from approximately 600 million to approximately 800 million years, CO2 concentrations will fall to levels too low to support plant photosynthesis. C3 photosynthesis, the form used by most plants, becomes impossible below approximately 150 parts per million. C4 photosynthesis, a more CO2 efficient variant, can persist to lower concentrations, but not indefinitely. When CO2 falls below photosynthetic thresholds, the base of the food web collapses, not gradually in a way that allows evolutionary adaptation, abruptly on geological timescales as the concentrations cross the minimum required for the biochemical reactions that power the biosphere. The result is the progressive collapse of complex life, first plants, then the animals that depend on them, eventually the simpler photosynthetic organisms that require even minimal CO2. The Earth will continue to have liquid water and a functioning atmosphere at this point. The conditions that we associate with habitability, liquid water, moderate temperatures, and atmosphere will still exist. But the biosphere as it currently exists, the interconnected web of organisms that has inhabited this planet for billions of years, will not survive the CO2 starvation that the brightening sun makes inevitable. This is approximately 600 million years from now, not tomorrow, not in any human timescale, but not geological infinity either. In the context of Earth's 4.5 billion year history, 600 million years is a significant fraction, about 13% of the planet's total age. Life on Earth has already existed for approximately 4 billion years. It has roughly 600 million years remaining in the form we would recognize. After the collapse of complex photosynthesis-dependent life, the planet continues, but stripped of its biosphere. A world with liquid water and moderate temperatures, but no meaningful biological activity. Habitable in the narrow physical sense, but biologically dead. Over the subsequent hundreds of millions of years, the sun continues brightening, temperatures rise further, and eventually, perhaps 1 to 1.5 billion years from now, the warming becomes severe enough that the oceans begin to evaporate. This is the terminal phase. Once oceans begin to evaporate significantly, water vapor enters the upper atmosphere where ultraviolet radiation dissociates it, splitting water molecules into hydrogen and oxygen. Hydrogen, being light, escapes to space. Oxygen reacts with surface rocks. The water is gone, permanently, irreversibly. Earth follows Venus into a moist greenhouse state, then into a runaway state, then into the dry, high-pressure inferno that the inner solar system's inner dead world has been for perhaps 700 million years. This is the physics. This is where Earth ends up regardless. Barring some extraordinary intervention, some technology or deliberate planetary engineering that could manage stellar output, or move Earth's orbit outward, or find some other way to extend the habitable window. The timeline is long, but the destination is fixed. Now let us return from this long view to the shorter view, to the mechanisms that operate on timescales that are not billions of years, but millions or thousands, and that represent real risks to the specific conditions that sustain the biosphere as it currently exists. The geological record is full of events in which the biosphere was significantly disrupted on relatively short timescales. The 5 major mass extinctions in Earth's history and the numerous smaller extinction events that punctuate the fossil record represent episodes in which the conditions for life changed faster than life could adapt, and large fractions of species were eliminated as a result. The end Permian extinction, the most severe in the fossil record, occurring approximately 252 million years ago, eliminated approximately 96% of marine species and 70% of terrestrial vertebrate species. It is sometimes called the Great Dying, and it nearly represented the complete collapse of complex animal life on Earth. The cause was volcanic, specifically the eruption of the Siberian Traps, one of the largest volcanic events in Earth's history, which over a period of perhaps 1 million years released enormous quantities of CO2, sulfur dioxide and other gases into the atmosphere, triggering rapid climate change, ocean acidification and the collapse of marine oxygen levels. The volcanic eruptions also ignited coal and gas deposits, adding further carbon to the atmosphere rapidly. The end Permian is the most extreme example, but it is not the only one. The end Cretaceous extinction 66 million years ago, the one that eliminated the non-avian dinosaurs, involved both the impact of a roughly 10-kilometre asteroid and simultaneous major volcanic eruptions from the Deccan Traps in what is now India. The combination of immediate impact effects and prolonged volcanic disruption produced a rapid and severe perturbation of the global climate system. The Paleocene-Eocene thermal maximum, approximately 56 million years ago, involved a rapid addition of carbon to the atmosphere. Estimates range from 2,000 to 10,000 billion metric tons released over a few thousand years, the source debated, that raised global temperatures by approximately 5 to 8 degrees Celsius over a few thousand years. This was not an extinction event of the scale of the end Permian, but it caused significant ecological disruption, ocean acidification, and the disappearance of numerous marine species. The pattern across these events is consistent. When carbon is added to the atmosphere rapidly, faster than the weathering cycle can compensate, temperatures rise, ocean chemistry changes, and ecosystems that evolved under stable conditions are disrupted in ways that many species do not survive. The rate matters. This is not an obvious point, and it deserves emphasis. A planet can eventually adjust to higher CO2 concentrations. The thermostat will draw CO2 down over millions of years and stabilize the climate at a new equilibrium. But the adjustment period involves significant disruption. Species that cannot adapt fast enough to the transitional conditions go extinct. Ecosystems that evolved under one set of conditions collapse when those conditions change faster than evolutionary processes can respond. The current rate of carbon addition to the atmosphere, approximately 37 billion metric tons per year, driven by fossil fuel combustion, deforestation, and industrial processes, is faster than any of the major carbon perturbation events in the geological record for which we have good rate estimates. The Paleocene-Eocene thermal maximum, which caused significant ecological disruption and is considered a rapid event in geological terms, released its carbon over several thousand years. Current emissions, if maintained, would add an equivalent amount of carbon in decades. This comparison does not mean current emissions will cause an end Permian scale extinction. The geological events that produced the major mass extinctions involved sustained volcanic activity over timescales of hundreds of thousands to millions of years, with total carbon additions that exceed anything in currently projected human emissions scenarios. The comparison is not about ultimate scale, it is about rate. And rate matters because ecosystems do not have time to adapt when conditions change quickly. The specific organisms, food webs, and ecological relationships that constitute the current biosphere evolved under conditions that have been relatively stable, by geological standards, for millions of years. Rapid change creates a mismatch between the conditions organisms are adapted to and the conditions they actually face. This mismatch is what extinction looks like from the inside. Let us now talk about something that is genuinely uncertain: about the specific question of tipping points and whether the Earth's climate system has thresholds beyond which self-reinforcing feedbacks take hold in ways that are difficult or impossible to reverse. The carbonate silicate thermostat is a stabilizing feedback. It counteracts perturbations and tends to return the system toward equilibrium. But not all feedbacks in the Earth system are stabilizing. Some are destabilizing. They amplify perturbations rather than counteracting them. The most significant destabilizing feedbacks currently being studied involve the behavior of large carbon reservoirs, stores of carbon that, if released, would add substantially to atmospheric CO2 concentrations and further warm the climate, potentially releasing more carbon in a self-reinforcing cycle. The Arctic permafrost contains approximately 1.5 trillion metric tons of organic carbon, the accumulated remains of vegetation and other organic material preserved in frozen ground for thousands to millions of years. As the Arctic warms and permafrost thaws, this carbon is exposed to microbial decomposition and is released to the atmosphere as CO2 and methane, both greenhouse gases. The warming releases carbon, which warms the climate further, which thaws more permafrost, which releases more carbon. The scale of the permafrost carbon reservoir, approximately twice the amount of carbon currently in the atmosphere, makes this feedback potentially significant. The specific dynamics of the permafrost carbon feedback are actively researched and still uncertain. The rate at which carbon is released as permafrost thaws, the fraction released as methane versus CO2, the degree to which warming in the deep layers of permafrost lags surface warming, and the potential for sudden releases from thermocast and other destabilization processes rather than gradual thawing. What can be said with confidence is that the permafrost feedback is not negligible, that thawing permafrost is already releasing measurable carbon, that the release is expected to increase as warming continues, and that the potential scale of the release is large enough to matter for climate projections on the scale of centuries. Methane hydrates, ice-like structures that trap methane in ocean sediments at specific temperature and pressure conditions, represent another large carbon reservoir. Warming of the deep ocean could, in principle, destabilize these structures and release their methane to the atmosphere. The current scientific consensus is that large-scale methane hydrate destabilization on short timescales is unlikely. The deep ocean warms slowly enough that the most vulnerable hydrates are limited. But the complete dynamics of this system are not fully characterized, and it remains a source of uncertainty in long-term projections. Ice sheet dynamics represent a different kind of tipping point concern. The Greenland and Antarctic ice sheets contain enough ice to raise global sea levels by approximately 65 meters if they melted completely. They are not going to melt completely on short timescales. The thermal inertia of ice sheets means their full response to warming takes centuries to millennia. But ice sheets can also exhibit threshold behavior, where a specific level of warming triggers dynamics that lead to substantially more melting than would occur in a simple linear response. The West Antarctic ice sheet, in particular, has a configuration with its base below sea level and sloping toward the ice sheet's interior that makes it potentially vulnerable to a feedback called marine ice sheet instability. Once a sufficient portion of the ice sheet is exposed to warm ocean water, the retreat of the grounding line, where the ice meets the ocean floor, can become self-sustaining, continuing even if external warming stops. Whether this process is already irreversibly underway for parts of West Antarctica is an active area of research and genuine scientific debate. The significance of these potential tipping points is not that any of them represents a guaranteed catastrophe. It is that they represent mechanisms by which the response to a given perturbation might be larger and less reversible than simple linear extrapolation would suggest. They represent the possibility that the Earth system has thresholds, specific conditions beyond which the behavior of the system changes qualitatively, not just quantitatively, and that crossing those thresholds produces consequences that persist on timescales much longer than the perturbation that triggered them. The scientific literature on planetary tipping points, a 2018 paper by Stefan and colleagues in the Proceedings of the National Academy of Sciences, has been particularly influential, identifies a set of interacting elements of the Earth system that, if sufficiently destabilized, could transition the planet to a substantially warmer state, and potentially to a trajectory toward further warming that would be difficult to reverse. This is sometimes called the hothouse Earth scenario, not a runaway Venus, but a planet stabilized at a much higher temperature than today, with substantially different conditions for life. Whether this scenario is likely and what temperature thresholds might trigger it is actively debated. The science is genuinely uncertain in ways that are important to acknowledge honestly. The uncertainty is not a reason for complacency. The consequences of the scenario, if it materialized, would be severe. But it is important to be accurate about what is known and what is not. Let us now talk about the specific evidence from other planets, from the missions that have studied Mars and Venus in detail, about what those worlds reveal about how planetary habitability ends, and what that reveals about Earth. MAVEN, the Mars Atmosphere and Volatile Evolution spacecraft, has been orbiting Mars since 2014 and has directly measured the current rate of atmospheric loss to the solar wind. The measurements confirm that Mars is losing approximately 100 grams of atmosphere per second to solar wind stripping, a rate that, integrated over billions of years, is consistent with the loss of a substantially thicker ancient atmosphere. MAVEN also measured enhanced atmospheric loss during a solar storm in 2015, demonstrating that the rate of loss is variable and that particularly energetic periods of solar activity accelerate the stripping. The MAVEN data provide direct physical confirmation of the mechanism that ended Mars's habitability, not as a theoretical reconstruction from surface geology, but as a real-time measurement of a process that has been operating for billions of years. The same process that stripped Mars's ancient atmosphere is still operating today, still removing material, still measurably reducing an atmosphere that is already a shadow of what it once was. The InSight lander, which operated on Mars from 2018 until 2022, when its solar panels became covered with dust and it could no longer generate power, provided the first direct seismic measurements of Mars's interior. The measurements revealed a Mars with a surprisingly large liquid core, larger than most models predicted, and a crust that is thicker and more complex than anticipated. The seismic data also revealed that Mars has detectable Marsquakes. The planet is not geologically dead in the absolute sense, but its activity is vastly lower than Earth's. The InSight data matter for the habitability question because they constrain the interior history that produced Mars's current state. A planet's internal heat budget determines how long it can sustain the convection that generates a magnetic field. The InSight measurements suggest that Mars's interior has cooled to a degree consistent with the early loss of its magnetic field. The seismic evidence is consistent with a planet that once had more internal activity and has been cooling and solidifying for billions of years. For Venus, the picture from the existing missions is less complete. The surface is poorly characterized at the resolution required to read its geological history in detail. The Magellan spacecraft mapped the Venusian surface with radar in the early 1990s, revealing a world of volcanic plains, vast lava flows, and distinctive geological features unlike anything on Earth. The crater density, relatively low compared to Mars or the Moon, suggested the surface was relatively young, consistent with the global resurfacing event approximately 300 to 700 million years ago. New missions to Venus are now in development. NASA's Da Vinci Plus mission will send an atmospheric probe that will descend through Venus's atmosphere, sampling its chemistry and eventually imaging the highlands, ancient terrain that may preserve records of an earlier Venus. NASA's Veritas mission will map the Venusian surface with significantly better resolution than Magellan, looking for signs of current volcanic activity and geological processes. The European Space Agency's Envision mission will study the planet at multiple wavelengths, looking at everything from the surface to the upper atmosphere. These missions will not return data for years, but when they do, they will provide the most detailed picture yet of how Venus became what it is, and by comparison will illuminate what Earth would need to do to avoid a similar trajectory. Let us now talk about what the comparison between Earth, Mars and Venus reveals at the level of general principle, about what conditions are necessary for a planet to sustain habitability over billions of years, and how many of those conditions Earth currently meets. The conditions that appear necessary, based on what Mars and Venus teach us, are roughly these: a strong global magnetic field to protect the atmosphere from stellar wind stripping, active plate tectonics or an equivalent recycling mechanism to sustain the carbonate silicate thermostat, an orbit within the habitable zone of the host star, where temperatures allow liquid water, but not so close that increased stellar luminosity triggers runaway warming, and not so far that the thermostat cannot compensate for declining temperatures. Sufficient internal heat to sustain the magnetic field and the tectonic system, and sufficient initial inventory of water and carbon to provide the raw materials for habitability. Earth currently meets all of these conditions. It has a strong magnetic field, it has active plate tectonics, it orbits within the habitable zone, it retains significant internal heat, it has abundant water and carbon. But none of these conditions is guaranteed to persist indefinitely. The magnetic field is sustained by convection in the liquid outer core, a process driven by the temperature difference between the hot inner core and the cooler mantle. As Earth continues to cool over billions of years, the inner core grows by solidification, and eventually, perhaps 1 to 2 billion years from now, the temperature difference driving convection may become insufficient to maintain a strong field. The magnetic field may weaken or become intermittent. Earth may gradually transition towards something more like the unprotected Mars. Plate tectonics depends on water in the mantle, water that lubricates the faults and subduction zones that make tectonic motion possible. As Earth ages and loses water through various processes, tectonic activity may slow and eventually stop. Without tectonics, the carbonate silicate thermostat breaks. Without the thermostat, the planet loses the mechanism that has regulated its climate for billions of years. None of these long-term changes is imminent. On human timescales, even on civilizational timescales measured in thousands of years, Earth's fundamental planetary systems are stable. The magnetic field, the tectonic system, the thermostat, these are not going anywhere in any time frame that is directly relevant to the decisions we make today. But here is the thing that the comparison with Mars and Venus makes clear. The conditions for planetary habitability are not guaranteed. They are contingent, dependent on specific physical processes that operate on specific timescales and that can be disrupted by specific mechanisms. Mars lost its magnetic field. Venus may have lost its climate stability. Earth will eventually lose both. The question is not whether, but when and how. And when we understand this, when we understand that habitability is a physical state that planets can exit, the question of Earth's current trajectory becomes more pointed. because the geological record shows that the biosphere, the specific living system that exists on Earth today, is more fragile than the planet's physical habitability. Planets can sustain liquid water and moderate temperatures and breathable atmospheres while losing most of their biological complexity. The 5 major mass extinctions in Earth's history each reduced the biosphere's complexity significantly, eliminating species, collapsing ecosystems, resetting evolutionary trajectories, while the planet remained physically habitable. The planet survived. The biosphere, in its specific configuration at the time, did not. Earth today is experiencing what geologists are beginning to characterize as a 6th major extinction event, a rapid loss of species at rates significantly above background extinction rates, driven by habitat destruction, climate change, pollution, overexploitation, and the cascading effects of these stressors on ecosystems. The specific magnitude and ultimate severity of this event are still unfolding and are not fully comparable to the major geological extinction events which involved global perturbations of the physical environment. But the direction is clear. What the comparison with Mars and Venus adds to this picture is a sense of the larger context. Earth is one of at least 2 planets in the solar system that appear to have been habitable and lost that habitability through specific physical processes. It is one of at least 2 that may have had rich biological chemistry for periods measured in hundreds of millions of years, then transitioned to states hostile to life. Earth sits in a trajectory that, on the scale of billions of years, leads to the same end. This does not make the current moment uniquely catastrophic in a cosmic sense. Planets lose habitability. This is normal planetary physics. It is not a tragedy from the universe's perspective. It is, however, the only home we have. And the universe's indifference to whether we maintain it is precisely why its maintenance depends on us. Let us now talk about what the universe more broadly looks like through the lens of this analysis, about what the pattern of planetary death tells us about the prevalence of life across the cosmos, and what it implies about the Fermi paradox. The Drake equation, the framework for estimating the number of communicating civilizations in the galaxy, includes a term for the fraction of habitable planets that actually develop life, and another for the fraction of life-bearing planets that develop intelligence. These terms are poorly constrained, and debates about them dominate discussions of extraterrestrial intelligence. But there is another term that receives less attention: the fraction of habitable planets that remain habitable long enough for complex life to develop. The development of complex multicellular life on Earth required approximately 3 billion years. 3 billion years of stable conditions maintained by the thermostat and the magnetic field and the tectonic system, during which simple life evolved and diversified and eventually produced the conditions for more complex forms. If the window of habitability on most potentially habitable planets is significantly shorter than this, if most planets that begin with habitable conditions lose them before complex life has time to evolve, then even a universe full of planets with early habitable conditions might contain very few planets with complex life. Mars may have been habitable for perhaps 500 million years, long enough for life to begin, perhaps, but probably not long enough for it to develop beyond microbial complexity, if the evolutionary timelines on Earth are any guide. Venus may have been habitable for 2 to 3 billion years, longer and potentially long enough for complex life to have had a chance. But by comparison to Earth's 4 billion year window of continuous habitability, even Venus's potentially generous window is shorter. And these are the 2 most similar planets to Earth in the solar system. If the pattern of habitability loss they represent is typical, if most terrestrial planets either lose their magnetic fields too early, or experience runaway warming from excessive stellar proximity, or lose their tectonic systems before the thermostat can fully compensate for stellar brightening, then the fraction of habitable-seeming planets that actually sustain conditions for complex life for billions of years may be small. This is not a new argument. The rare Earth hypothesis, developed by Peter Ward and Joe Kirschvink and others, makes a version of this case. But what the Mars and Venus data add is specificity, not just the theoretical argument that planetary habitability is contingent, but the empirical demonstration in our own solar system that habitability loss has actually occurred in at least two distinct ways on planets that started with what appeared to be favorable conditions. The universe may indeed be full of worlds that began with promise. Worlds where chemistry started, where simple organisms took hold, where the basic requirements were met, and then lost the conditions that would have allowed those beginnings to develop into anything more. Dead worlds. Not dramatically destroyed, not catastrophically ended, but quietly, gradually, inevitably transitioned out of the states that made life possible. The question of whether Earth is next, whether it belongs in the company of the living, or is already beginning the transition toward the dead, depends on which timescale you examine. On the timescale of the Sun's evolution, the answer is unambiguous. Earth is next. The timeline is billions of years, but the destination is certain. On the timescale of the current biological crisis, of the rapid changes in atmospheric chemistry and climate and ecosystems that characterize the present moment, the answer is more uncertain, more contested, and more dependent on choices that have not yet been made. The universe has given Earth an extraordinary run. 4 billion years of liquid water, of evolving chemistry, of increasingly complex life. 4 billion years of the specific set of physical conditions, the magnetic field, the thermostat, the tectonic system, that have kept this planet in the narrow band of conditions compatible with the biosphere's existence. But the universe has given other worlds extraordinary runs too, and those runs ended. Let us talk about something that rarely appears in discussions of planetary habitability, but that the evidence demands we consider: the specific role that life itself has played in maintaining Earth's habitability, and what this implies about the relationship between the biosphere and the physical conditions it depends on. The standard framing treats life as a passenger on a habitable planet. The planet provides the conditions: liquid water, moderate temperatures, suitable chemistry, and life takes advantage of them. In this framing, planetary habitability is a physical property of the planet, and life is something that happens within it. The evidence increasingly suggests this framing is incomplete. Life does not merely inhabit Earth's conditions. Life participates in creating and maintaining them. The relationship between the biosphere and the physical Earth is not one-directional, but deeply reciprocal. And this reciprocity has profound implications for understanding what happens when the biosphere is significantly disrupted. The most important example is oxygen. Earth's atmosphere contains approximately 21% oxygen, a concentration that has no precedent in the physical chemistry of planetary atmospheres without biology. Oxygen is a highly reactive gas that combines readily with other materials. In the absence of continuous biological production, oxygen in the atmosphere would be consumed by reactions with rocks, volcanic gases, and organic compounds within geologically short timescales. The atmospheric oxygen we breathe exists only because photosynthetic organisms continuously produce it, at a rate sufficient to compensate for all the processes that remove it. The Great Oxidation Event, approximately 2.4 billion years ago, was one of the most significant transitions in Earth's history. The point at which photosynthetic life had produced enough oxygen to saturate the sinks that had been absorbing it and began to accumulate it in the atmosphere. This was, from one perspective, the largest pollution event in Earth's history, a biological transformation of the atmospheric chemistry that was profoundly toxic to the anaerobic organisms that had previously dominated. It was also the event that made complex animal life eventually possible, by providing the oxidizing atmosphere that powers the high-energy metabolism of animals. The biosphere did not merely adapt to Earth's chemistry, it transformed it in ways that made subsequent life possible. The oxygen that supports complex life is itself a product of life. The conditions that made animals possible were created by the organisms that preceded them. This reciprocity extends to other aspects of Earth's chemistry. The carbon cycle, the carbonate-silicate thermostat we have already discussed, involves biological processes at every step. Chemical weathering is significantly enhanced by biological activity. The presence of organic acids, root systems, and soil microbiomes accelerates the weathering of silicate rocks by orders of magnitude compared to purely abiotic weathering. The deposition of carbon as calcium carbonate in ocean sediments is primarily driven by organisms, marine organisms that build shells and skeletons of calcium carbonate, die, and sink to the ocean floor, creating the limestone deposits that eventually ride the tectonic conveyor belt into subduction zones. Without biology, the carbonate-silicate thermostat operates more slowly and less efficiently. With biology, it operates at the rate required to maintain climate stability in the face of the brightening sun. Life is not just a passenger in Earth's climate system, it is part of the mechanism that keeps the climate stable enough for life to persist. The nitrogen cycle, the set of processes that maintain atmospheric nitrogen at its current concentration and that make nitrogen available to living organisms, is almost entirely driven by biological processes. Nitrogen-fixing bacteria convert atmospheric N2 into forms usable by other organisms. Denitrifying bacteria convert nitrogen compounds back to N2. Without these biological processes, the nitrogen cycle would function very differently, with significant consequences for atmospheric chemistry and climate. The phosphorus cycle, the availability of phosphorus, a critical nutrient for all life, is substantially mediated by biological activity. The distribution of phosphorus between rocks, soils, water, and organisms depends on biological weathering, biological uptake, and biological decomposition in ways that determine the availability of this essential nutrient across the entire biosphere. The point is not that biology controls everything. It does not. But biology is woven into the operation of the systems that maintain Earth's habitability, in ways that make the biosphere and the physical Earth a single, coupled system, rather than a planet and its passengers. The Gaia hypothesis, James Lovelock's proposal that the Earth's living and non-living components constitute a self-regulating system that maintains conditions favourable for life, in its strong form overstates the intentionality of this coupling. But the weak form of the insight, that life is a significant component of the Earth system and that disrupting it disrupts the system, has become mainstream Earth science. What this means for thinking about the current biological crisis is significant. If the biosphere is not just a passenger on a habitable planet, but a functional component of the systems that maintain habitability, if removing significant biological complexity from the system degrades the function of those systems, then the mass extinction currently underway is not just an ethical concern about the loss of species. It is a functional concern about the integrity of the Earth system itself. The specific mechanisms by which biodiversity loss affects Earth system function are studied in the field of ecosystem services, the ways in which functioning ecosystems contribute to the physical and chemical processes that support all life, including human life. These services include the regulation of the water cycle through plant transpiration, the maintenance of soil fertility through the biological activity of soil organisms, the regulation of atmospheric composition through photosynthesis and decomposition, the stabilization of coastlines and watersheds through the physical presence of organisms, and many others. As species are lost and ecosystems are simplified, as biodiversity decreases and the complexity of biological communities diminishes, these services are degraded. Not catastrophically in most cases at current levels of loss, but measurably and in directions that compound over time. A biosphere that has lost significant diversity is a biosphere that performs the functions sustaining habitability less reliably, with less redundancy, with less capacity to respond to novel stresses, with less resilience to perturbation. Now let us talk about exoplanets, about what the last 2 decades of planetary science beyond the solar system have revealed about the prevalence of potentially habitable worlds, and what this tells us about where Earth sits in the broader cosmic picture. In 1992, the first confirmed detection of planets orbiting another star was announced. Planets around a pulsar, not a main sequence star, but confirmed planets nonetheless. In 1995, the first planet orbiting a main sequence star, 51 Pegasi b, a hot Jupiter with an orbital period of 4.2 days, was detected. These detections were proofs of concept, demonstrations that planets exist beyond the solar system and that we can find them. The Kepler Space Telescope, launched in 2009 and observing until 2018, transformed planetary science by detecting thousands of planets around other stars through the transit method, detecting the tiny dimming of a star's light as a planet passes in front of it. Kepler's planet catalogue now contains more than 2,600 confirmed planets, with thousands of additional candidates awaiting confirmation. The mission revealed that planets are extraordinarily common, that most stars have planets, that small rocky planets are more common than large gas giants, and that a significant fraction of Sun-like stars have planets in the habitable zone. The habitable zone, the range of orbital distances at which a planet receives enough stellar energy to maintain liquid surface water, but not so much that a runaway greenhouse is triggered, is an imprecise concept because its boundaries depend on assumptions about atmospheric composition, cloud cover, and other factors. But using conservative estimates of the habitable zone, the fraction of Sun-like stars with potentially habitable rocky planets is roughly 10 to 20%. There are approximately 100 billion Sun-like stars in the Milky Way. The arithmetic produces a number of potentially habitable planets in the galaxy that is staggering. Hundreds of millions to billions, depending on assumptions. The TESS mission, the Transiting Exoplanet Survey satellite, launched in 2018, has extended the Kepler survey to cover the entire sky and is finding habitable zone planets around the nearest stars, making them candidates for detailed characterization. The James Webb Space Telescope, launched in 2021, is beginning to characterize the atmospheres of some of these planets, looking for specific molecular signatures in transmission spectra that might indicate atmospheric composition and potentially biological activity. What these observations reveal is not that Earth is unique as a potentially habitable planet. There are, by all indications, an enormous number of planets with the basic physical requirements for habitability. What they do not reveal, what they cannot yet reveal with current technology, is which of these planets actually hosts life, or how long their habitability has persisted. This is where the lessons of Mars and Venus become cosmically relevant. A planet that appears potentially habitable from its orbital parameters and stellar environment may have transitioned out of a habitable state millions or billions of years ago through the same mechanisms that ended Mars's and Venus's habitability. From our vantage point, without detailed atmospheric characterization, we cannot distinguish a planet that has been habitable for 4 billion years from one that was habitable for 500 million years and has been a frozen desert ever since. The number of currently habitable planets, planets with conditions that support active living biospheres at this moment, may be significantly smaller than the number of potentially habitable planets, because some fraction of seemingly habitable worlds will have experienced the transitions that Mars and Venus experienced. How large that fraction is depends on how common the specific conditions that sustained Earth's long-term habitability actually are. The magnetic field, the plate tectonics, the precise orbital position, the specific history that avoided the transitions that ended Mars's and Venus's habitability. We do not know this fraction. We have one planet with sustained long-term habitability and multiple nearby examples of habitability loss. The sample is too small to establish a reliable rate. But the examples that exist, Mars and Venus, the two most Earth-like planets in the solar system, both appear to have lost or degraded their habitability. This is consistent with the possibility that long-term habitability is unusual, that most planets in the habitable zone transition out of it on timescales shorter than required for complex life. It is also possible that Mars and Venus are unrepresentative cases, that the specific factors that ended their habitability are uncommon, and that most habitable zone planets sustain conditions for billions of years. We genuinely do not know. The data are insufficient to distinguish these possibilities. What we do know is that Earth sits at a specific and possibly unusual confluence of favourable conditions. The magnetic field, the thermostat, the tectonic system, the orbital parameters, the atmospheric composition, that has sustained habitability longer than the examples we can examine from nearby. Whether this makes Earth unusual in the galaxy, or merely one of many similarly fortunate worlds, is an open question. But it makes Earth valuable. Valuable in the specific sense of representing a physical state that is, by the evidence of our solar system, not guaranteed. Let us now talk about what the timescales of planetary habitability loss imply for the question of intelligence and civilization in the universe, about the relationship between the window of habitability and the time required to produce technological civilizations. Complex life on Earth took approximately 3 billion years to develop from the first unicellular organisms. Technological civilization, in any form that involves the capacity to understand its own planetary situation, has existed for perhaps a few thousand years. The ratio of the time required to produce civilization to the time available under sustained habitability is approximately 0.001%. Civilization appeared very late in Earth's habitable window, with very little time remaining by cosmic standards. If this ratio is typical, if civilizations generally arise late in their planet's habitable window, close to the transitions that will end or degrade habitability, then the window between the emergence of a civilization capable of understanding its situation and the degradation of the conditions it depends on may be short. Not inevitably short. There is no physical law that says civilizations must arise late. But the evidence from Earth suggests that the process is slow, that it takes a large fraction of the available habitable window to produce intelligence, which means that the remaining window, after intelligence appears, may typically be modest. This has an implication for the Fermi paradox that is rarely drawn explicitly. Even if intelligent life is common, civilizations capable of becoming multiplanetary or interstellar may face a race against the degradation of their home world's habitability. The window for developing the capability to expand beyond the home world, and for doing so before the conditions at the home world deteriorate significantly, may be narrow. Civilizations that fail to expand in time may find themselves trapped on worlds that are progressively less capable of supporting them, without the technological development required to move elsewhere. This is not Earth's situation on any short time scale. Earth's fundamental habitability, its liquid water, its functional atmosphere, its moderate temperatures, is not at immediate risk from the long-term planetary processes we have discussed. The CO2 starvation of photosynthesis is hundreds of millions of years away. The loss of the magnetic field and tectonic system is billions of years away. These are not urgent threats in any human sense. But the biosphere's specific current configuration, the ecosystems and species and ecological relationships that constitute the living world as it exists today, is more fragile than the planet's physical habitability. The biological disruptions of the current era do not threaten the planet's long-term physical habitability. They threaten the specific biological heritage of 4 billion years of evolution, and they threaten the ecosystem services that the current biosphere provides to the civilizations that depend on it. Let us now talk about what the dead worlds of the solar system teach us about what makes the difference, about why Earth has maintained its conditions when Mars and Venus did not, and what this reveals about what we should be paying attention to. The difference between Earth and Mars is, at its core, a difference of size and internal heat. Mars is smaller, approximately half Earth's diameter and about 10% of Earth's mass. A smaller planet has less internal heat to begin with because the amount of radioactive material generating heat scales approximately with mass. A smaller planet also has a higher surface area to volume ratio, meaning it loses its internal heat to space more quickly. Mars cooled faster than Earth. Its magnetic field died sooner. Its tectonic activity slowed and stopped sooner. The processes that sustain habitability, the magnetic field, the thermostat, the recycling of carbon, depend on internal heat, and Mars ran out of the internal heat to sustain them on a timescale shorter than required for complex life to develop. The difference between Earth and Venus is subtler and less well understood because Venus is almost the same size as Earth and should have had a similar internal heat budget. The current best hypothesis for the Venus divergence involves the interaction between orbital distance, stellar luminosity, and climate stability. Specifically, the possibility that Venus was close enough to the Sun that, once solar luminosity reached a critical level, positive climate feedbacks overwhelmed the thermostat, and the planet transitioned to its current state. Earth, being farther from the Sun, has a larger margin before reaching that critical threshold. But the margin is finite, and it narrows as the Sun brightens. What Earth has that Mars lacks is size, enough internal heat to sustain the magnetic field and plate tectonics for billions of years. What Earth has that Venus may lack is orbital distance, enough separation from the Sun to remain below the threshold for runaway warming even as the Sun brightens. Both of these are physical properties of the planet, properties that were set at formation and that cannot be changed by any process operating from within the planet. The lesson is that planetary habitability is, at its foundation, a function of physical properties, size, orbital distance, stellar type, that are determined at formation and that change only slowly over geological time. Earth is habitable because it formed at the right size and the right distance from the right star. This is partly chance and partly the consequence of processes that we are still working to understand. But there is a second lesson, less obvious and more relevant to the current moment. Within the window of physical habitability, the specific state of the biosphere matters. The planet may remain physically capable of supporting life while losing the specific biological complexity that makes the current world what it is. The mass extinctions of the geological past demonstrate this, Earth remained physically habitable through the end Permian, the end Cretaceous, and all the other extinction events. But the biosphere that existed before each event was not the biosphere that existed after it. Complexity was lost. It was eventually recovered, evolution continued, new species filled the empty niches, new ecosystems developed. But the recovery took millions of years, and what recovered was not what was lost. We are in the middle of such an event now. Not the most severe in Earth's history, not yet, not in terms of total species loss, but one with a distinctive character, a rate of change faster than the geological record documents for most comparable events, and a cause that is, for the first time in Earth's history, primarily biological, driven by the activity of a single species. This is the specific way in which Earth might be next, not in the sense of losing its physical habitability on any timescale relevant to human civilization, but in the sense of losing the specific biological configuration that has existed for millions of years and that sustains the conditions on which human civilization depends. Let us now talk about the detection of biosignatures on exoplanets, about what the James Webb Space Telescope and future missions might reveal about life elsewhere, and what that would tell us about Earth's place in the universe. The James Webb Space Telescope has the capability to detect atmospheric signatures of transiting exoplanets, planets that pass in front of their host star from our perspective, allowing starlight filtered through the planet's atmosphere to be analysed spectroscopically. By comparing the spectrum of the star's light transmitted through the atmosphere with the spectrum without the planet, scientists can identify molecules that absorb at specific wavelengths: water vapour, carbon dioxide, methane, oxygen, ozone. Some of these molecules are particularly interesting as potential biosignatures, indicators of biological activity. Oxygen in abundance combined with methane is the classic biosignature pair. Both gases react with each other and would quickly disappear from an atmosphere in the absence of continuous biological production. Finding both in significant quantities simultaneously would be difficult to explain without life. Nitrous oxide, produced primarily by microbial activity, is another potential biosignature. The specific combination and ratio of gases can, in principle, indicate a biologically active atmosphere. Webb has already obtained the first transmission spectra of potentially habitable exoplanets, most notably the 7 planets of the TRAPPIST-1 system, 7 rocky planets orbiting an ultra-cool red dwarf approximately 40 light-years away, 3 of which are in the system's habitable zone. Initial Webb observations of TRAPPIST-1b, the innermost planet, were consistent with the absence of a substantial atmosphere, at least of the dense CO2-dominated variety that would be a preliminary indicator of habitability. But the habitable zone planets have not yet been fully characterized, and the observations required to detect biological signatures, if they exist, will require significantly more telescope time than has yet been allocated. The honest assessment is that Webb can make progress on characterizing potentially habitable exoplanet atmospheres, but definitive detection of biosignatures is at the edge of its capabilities for most plausible scenarios. The planets most amenable to atmospheric characterization are those orbiting the smallest, coolest stars, red dwarfs, because these stars produce less flux relative to the planet's atmospheric signal. But red dwarf planets present their own habitability challenges. The planets must orbit close to the star to be in the habitable zone, making them potentially tidally locked and subject to intense stellar flares and high ultraviolet radiation. What a confirmed detection of biosignatures on another planet would mean for our understanding of Earth and life in the universe is difficult to overstate. It would establish that the specific conditions that led to life on Earth, whatever those conditions precisely were, are not unique. That the chemistry of life arises in at least some other worlds given the right conditions. It would transform the question from whether life is rare to how common it is. What the absence of detectable biosignatures after sufficient characterization of a significant sample of potentially habitable planets would mean is equally significant, though more ambiguous. Absence of detection is not proof of absence, but a systematic absence of biological signatures in a large sample of potentially habitable worlds would be consistent with life being rare, with the habitable window being shorter than required for life to develop on most worlds, with some other filter that prevents life from reaching the complexity required to produce detectable biosignatures. Either outcome, detection or systematic non-detection, would be enormously informative about Earth's place in the universe and about what the cosmic prevalence of life implies for the Fermi paradox and for the question of whether we are alone. Let us now talk about what all of this implies for the specific question the title poses, about whether the universe is full of dead worlds and whether Earth is next. The evidence from the solar system is clear. The universe contains worlds that were once habitable and are now not. Mars and Venus are the examples closest to hand, two worlds with the physical prerequisites for habitability that appear to have lost or severely degraded those conditions through mechanisms that are now well understood. The mechanisms are not exotic. They are the normal physics of planetary evolution: internal cooling, atmospheric loss, climate feedback, operating on timescales measured in hundreds of millions to billions of years. The evidence from exoplanet surveys suggests that habitable zone planets are common, that the physical prerequisites for habitability are met by a large fraction of the planets in the galaxy. But physical prerequisites are necessary, not sufficient. A planet with the right orbital distance and the right size and the right star may still lose its magnetic field, or experience a runaway greenhouse, or undergo a catastrophic volcanic resurfacing event, or suffer some other transition that ends or severely degrades habitability. We do not know what fraction of potentially habitable planets remain habitable long enough for complex life to develop. We know from the solar system that the fraction is not 100%. At least 2 out of 3 potentially habitable inner solar system planets appear to have lost their habitability, though the sample is tiny and the comparison is complicated by the specific physical differences between the 3 worlds. Whether the universe is full of dead worlds, whether the typical fate of a potentially habitable planet is to lose habitability before complex life has a chance to develop, is a question that current evidence cannot definitively answer. It is consistent with the evidence. It is also consistent with the evidence that many worlds sustain habitability long enough for life to develop, and that life is common throughout the galaxy. What the evidence does establish is that habitability is not guaranteed, that it is a physical state that planets can and do exit through specific mechanisms, and that the duration of habitability varies and is not always sufficient for complex life. Is Earth next? In the long-term physical sense, the CO2 starvation of photosynthesis, the eventual loss of the magnetic field and plate tectonics, the engulfment by the expanding sun, yes, Earth is next. The timeline is hundreds of millions to billions of years, but the destination is certain. Earth will join Mars and Venus as a world that was once habitable and is not. But in the shorter-term sense, the sense relevant to the current biological crisis and the current rapid changes in atmospheric chemistry and climate, the question is different. Earth is not at risk of losing its physical habitability in any timescale relevant to human civilization. The planet will have liquid water and a functional atmosphere for hundreds of millions of years, regardless of what human civilization does or fails to do. What is at risk is the specific biological configuration, the particular set of ecosystems, species, and ecological relationships that has developed over millions of years and that sustains the conditions for human civilization in particular. The rapid changes of the current era do not threaten the planet. They threaten the biosphere's current configuration, and with it, the ecosystem services that civilization depends on. This is a narrower claim than planetary habitability loss, happening on timescales that are not geological but historical. Not millions of years, but decades and centuries. Not the slow drift of planetary systems, but the rapid disruption of biological ones. Let us talk about what that disruption looks like concretely, about the specific mechanisms by which the current biological crisis operates, and why they are different in character from the planetary processes we have been discussing. The 5 major mass extinctions in Earth's history were driven by physical perturbations, large impacts, massive volcanic episodes, rapid changes in ocean chemistry that disrupted the physical conditions in which organisms lived. The biology died because the physics changed. The organisms did not choose to eliminate themselves. They were eliminated by circumstances external to their biology. The current extinction event is different in a specific and historically unprecedented way. It is driven primarily by the activity of one species, Homo sapiens, acting on the rest of the biosphere through a set of mechanisms that are, individually and in combination, reducing the diversity and complexity of life on Earth at rates that significantly exceed background extinction rates. Habitat destruction is the most direct mechanism. The conversion of natural ecosystems to agricultural land, urban development, and other human uses eliminates the physical space in which wild species live. A species without sufficient habitat goes extinct, not through any process of direct elimination, but through the simple arithmetic of ecological minimum area requirements. There is a threshold established by island biogeography and ecological theory and confirmed by empirical data, below which a habitat fragment cannot support the species composition of the larger ecosystem from which it was derived. As habitats are fragmented and reduced, species are lost in a predictable, measurable way. Approximately 50% of Earth's land area has been significantly modified by human activity, converted to agriculture, developed, or otherwise substantially altered from its natural state. The area of natural ecosystems, sufficient in size to sustain large, intact ecological communities, has shrunk dramatically over the past several centuries. The Amazon basin, the Congo basin, the boreal forests of Canada and Russia, the tropical forests of Southeast Asia, these are the remaining large areas where intact ecological communities persist, and all of them are under active pressure from development and resource extraction. Climate change operates on the biosphere through multiple mechanisms simultaneously. Species whose ranges are determined by temperature and precipitation patterns face shifting conditions that move the suitable range outside their current distribution. For some species, the shift is fast enough and the suitable range accessible enough that range shifts can keep pace with changing conditions. For others, species with limited dispersal ability, species whose habitat is fragmented, species at the poles or at high altitudes with nowhere further to go, range shifts are impossible, and the changing conditions represent a direct threat to survival. Climate change also disrupts the phenological relationships, the timing of biological events that structure ecological communities. If the timing of flowering shifts with warming temperatures, but the timing of the insects that pollinate those flowers does not shift equivalently, the plants fail to reproduce. If the timing of prey availability shifts, but the timing of predator breeding season does not, predator survival is compromised. These phenological mismatches, disruptions to the intricate timing relationships between species in a community, can collapse ecological relationships faster than changes in physical habitat alone. Ocean acidification, the reduction of ocean pH from the absorption of CO2 by seawater, directly affects marine organisms that build shells or skeletons of calcium carbonate. The chemistry is straightforward. More CO2 in the atmosphere means more CO2 dissolved in surface water, which means lower pH, which means lower carbonate saturation, which means more difficulty for calcifying organisms, corals, mollusks, echinoderms, some plankton, to build and maintain their structures. Ocean pH has already declined by approximately 0.1 units since pre-industrial times, a 26% increase in hydrogen ion concentration, and is projected to decline further as atmospheric CO2 continues to rise. Coral reefs are particularly vulnerable because they are built by calcifying organisms, corals, and are highly temperature sensitive. Coral bleaching, the expulsion of the photosynthetic symbionts that give corals their color and provide much of their energy, occurs when water temperatures exceed the thermal tolerance of the symbiosis by even a fraction of a degree Celsius over sustained periods. Bleached corals can survive and recover if temperatures return to normal within weeks. Prolonged bleaching leads to coral death. The Great Barrier Reef has experienced mass bleaching events in 2016, 2017, 2020, 2022 and 2024, a frequency that has increased dramatically compared to historical records, and that is occurring faster than recovery can take place. Coral reefs cover less than 1% of the ocean floor, but support approximately 25% of all marine species, providing habitat, feeding grounds, and nursery areas for an extraordinary diversity of fish, invertebrates, and other organisms. The loss of coral reefs at the scale currently occurring is not merely the loss of a beautiful ecosystem, it is the elimination of habitat that supports a quarter of the ocean's biodiversity. Overexploitation, the harvesting of species faster than they can reproduce, has historically been the most direct cause of species extinction, particularly for large vertebrates. The megafaunal extinctions of the Pleistocene, the loss of mammoths, mastodons, giant sloths, and dozens of other large mammals coinciding with the spread of human hunters across previously uninhabited continents, represent the first global wave of human-caused extinction, preceding agriculture and industrialization by thousands of years. Current overexploitation primarily affects marine fisheries, where catches have declined substantially from historical levels, despite increased fishing effort, indicating that populations have been reduced below sustainable levels. Invasive species, organisms introduced to regions where they have no evolutionary history, often by human transport, can devastate ecological communities by preying on species with no defenses against them, outcompeting native species, or transforming the physical structure of the habitat. Island ecosystems are particularly vulnerable. Species that evolved in isolation without mammalian predators are defenseless against introduced rats, cats, mongooses, and other predators. The extinction of the majority of the endemic bird species of Pacific Islands over the past several thousand years was primarily driven by the introduced species that arrived with human colonizers. These mechanisms interact and compound each other. A species stressed by climate change is more vulnerable to overexploitation. A habitat fragmented by development is more vulnerable to invasion by non-native species. A biologically simplified ecosystem, one that has lost species through any of these mechanisms, is less resilient to all other stresses, because resilience in ecological systems depends on redundancy, on the presence of multiple species capable of performing the same ecological function, so that if one is lost, the function continues. What the current extinction event represents is not a single perturbation, but the simultaneous operation of multiple stresses across most of the biosphere, interacting in ways that compound the effect of each individual stress. This is different from the great extinctions of the geological past, which were generally driven by single dominant physical causes operating globally: an impact, a volcanic episode, an ocean anoxic event. The current crisis is diffuse, multi-causal, and driven by the cumulative effect of human activity across every ecosystem on the planet. Let us now talk about something that the comparison with Mars and Venus illuminates in a specific way: the question of irreversibility, of which changes are recoverable and which are not, and why this distinction matters enormously for how we think about the current biological crisis. Mars lost its magnetic field approximately 4 billion years ago. The loss was irreversible on any timescale relevant to life. Once the field died, it stayed dead, because the internal heat required to sustain it had been irreversibly lost. The atmospheric stripping that followed was gradual but cumulative. Each year's loss added to the total, and what was lost could not be recovered from within the planet's own resources. Venus may have lost its oceans to a runaway greenhouse. If so, the loss was irreversible in any practical sense. Recovering a runaway greenhouse state requires either removing the source of greenhouse forcing at a rate faster than the feedback can compensate, or some external intervention of a scale that no natural process provides. Once the water was dissociated and the hydrogen escaped to space, the water was gone permanently. The lesson of planetary death, the specific lesson relevant to thinking about Earth's current situation, is that some planetary transitions are irreversible on any timescale relevant to life, while others are recoverable given sufficient time. Mars and Venus illustrate the irreversible cases. The geological record of Earth's own past illustrates that some major disruptions, while severe, are recoverable. The biosphere has been dramatically reduced multiple times and has recovered, each time producing a new configuration of species and ecosystems adapted to post-extinction conditions. But recovery from mass extinction takes millions of years. The fossil record shows that full recovery of biological diversity after a major extinction event typically takes 5 to 10 million years. Recovery of species richness, ecological complexity, and the full range of functional types. The recovery is real. Life is resilient at geological timescales, but the window between the extinction and the recovery is measured in millions of years. This means that the distinction between recoverable and irreversible for the current biological crisis is a question of timescale. The planet will eventually recover whatever biological complexity is lost in the current extinction event, but the recovery will take millions of years. Civilization and the specific conditions that sustain civilization exists on a timescale of thousands of years at most, far shorter than the recovery time for a major extinction event. From civilization's perspective, the loss of significant biological complexity over the next few centuries is functionally irreversible, even though from the planet's perspective it is eventually recoverable. The organisms that are lost cannot be recovered on timescales relevant to human civilization. The ecosystem services they provided, the regulation of water cycles, the maintenance of soil fertility, the carbon sequestration, the pest control, the pollination, cannot be recovered on timescales relevant to human civilization. This is the specific sense in which the current biological crisis constitutes an existential risk for civilization, not for the planet, not for life itself, but for the specific configuration of conditions that makes complex technological civilization possible. A biosphere with significantly reduced diversity and complexity provides ecosystem services less reliably, with less resilience to perturbation, with less capacity to buffer the impacts of other stresses. A civilization dependent on those services is proportionally more vulnerable. Let us now talk about what makes this moment specifically critical, about why the choices made in the next few decades have an outsized influence on the trajectory of the biological crisis compared to choices made before or after. The biology of extinction has a specific property that makes the current window critical in a way that the future will not be. Most of the species currently at risk, those whose populations have been reduced to levels where extinction risk is elevated, are not yet extinct. They exist in small, fragmented, stressed populations. The critical question for many of them is whether those populations can be stabilized, whether the habitats they depend on can be protected or restored, whether the pressures acting on them can be reduced. Extinction risk is not linear. A population reduced to 1,000 individuals is not merely more at risk than a population of 10,000. It faces a qualitatively different kind of risk, because at small population sizes, stochastic processes, random variation in births, deaths, and reproductive success, can drive a population to extinction even in the absence of any additional external pressure. This is called the minimum viable population problem, and it means that once a population falls below a threshold, recovery becomes increasingly difficult, even if external pressures are removed. Many of the world's most iconic and ecologically important species are at or approaching this threshold. Large mammals, birds of prey, sharks and rays, large reef fish, amphibians. Across many groups, the combination of habitat loss, overexploitation, climate change, and other stressors has reduced populations to levels where stochastic extinction risk is significant. The decisions made in the next few decades, whether remaining habitat is protected or converted, whether harvesting pressure is reduced or maintained, whether climate action is sufficient to limit the most severe temperature changes, will determine whether many of these species persist or are lost. This is the specific way in which the current moment is critical, not because it is the last moment at which action is possible. Species conservation has been successful in many cases, and there is no absolute deadline beyond which nothing can be done. But because the populations that currently exist are the last chance for maintaining the genetic diversity, the ecological relationships, and the evolutionary heritage that those species represent. Once a species is extinct, it is gone permanently, not for millions of years, but forever. The recovery of biological diversity after the current extinction event, whenever it occurs, will not include those specific species. It will include whatever new forms evolve to fill the ecological space left by their absence. Let us now talk about what all of this means at the largest scale, about the relationship between Earth's place in the cosmic context of planetary habitability and the specific choices that human civilization faces in the current era. The universe is full of planets, worlds with the physical prerequisites for liquid water and moderate temperatures and the chemical conditions required for life's chemistry. Whether it is full of worlds where that potential was realized, where life actually took hold, where complex organisms evolved, where intelligence eventually emerged, is the question that planetary science and astrobiology are working to answer, and that the James Webb Space Telescope and its successors may begin to constrain within our lifetimes. What Mars and Venus reveal, what the solar system's internal history of habitability loss demonstrates, is that the potential is not always realized. Worlds that begin with promise can and do transition out of the states that make life possible. The mechanisms are well understood. They are not rare or exotic. They are the normal consequences of planetary physics playing out over timescales that are long by human standards, but brief by cosmic ones. If the pattern the solar system reveals is typical, if most potentially habitable planets lose their habitability before complex life has time to develop, then the universe is full of dead worlds, or worlds that were briefly alive and are now dead. Not dramatically destroyed, not catastrophically ended, but quietly, inevitably transitioned out of the states that made life possible. Mars is the image of this. A world that had rivers and lakes and warm chemistry and possibly the beginnings of life. Now a frozen desert where the ancient river valleys are preserved like photographs of a world that no longer exists. If Earth is next, and in the long-term physical sense it is, then the question becomes what the window means. What does it mean to exist on a habitable world in the middle of its habitable period? After billions of years of stable conditions have produced extraordinary biological complexity, and before the planetary processes that will eventually end that complexity have fully asserted themselves. It means something specific. It means that the complexity that currently exists, the 8.7 million estimated species on Earth, the intricate ecological relationships between them, the evolutionary heritage of 4 billion years of biological development, is the product of an extraordinary process that played out over an extraordinary span of time under conditions that, by the evidence of the solar system, are not guaranteed. It means that this complexity exists in a window, bounded on the far side by the planet's long-term physical evolution, bounded on the near side by the rapidity of the changes currently underway. The window is real. The biological complexity inside it is real. The mechanisms that threaten to close the window, both the long-term planetary ones and the near-term anthropogenic ones, are real. And the choices that determine how much of that complexity persists through the current period of rapid change are being made now, in the decades between the beginning of the Industrial Revolution and whatever stabilization of human impact eventually occurs. This is what it means to say the universe might be full of dead worlds, and Earth is next. Not that catastrophe is certain, not that the trajectory is fixed, but that the specific combination of circumstances that produced the extraordinary biological world we inhabit, 4 billion years of maintained habitability, the full sweep of evolutionary diversification, the intricate web of ecological relationships that sustains all of it, is precious in a way that the cosmic context makes clear. Precious not in a sentimental sense, but in a physical one. In the sense of being the product of conditions that are, by the evidence available, not guaranteed. In the sense of being fragile in ways that the comparison with Mars and Venus makes specific. In the sense of being, in all probability, rarer than the number of planets in the galaxy might naively suggest. Let us now talk about what the scientific research agenda looks like from this perspective, about what we need to know to better understand how common habitable worlds are, how long their habitability persists, and what determines whether life develops within the window that habitability provides. The most direct way to constrain the prevalence of life in the galaxy is to characterize the atmospheres of potentially habitable exoplanets in sufficient detail to look for biosignatures. The James Webb Space Telescope has begun this work. It has detected CO2 in exoplanet atmospheres for the first time, demonstrating the capability that will be required. But Webb's capabilities are sufficient to detect biosignatures only for the most favorable targets, planets orbiting the smallest stars, which produce the highest planet-to-star contrast ratios. The next generation of ground-based telescopes, the Extremely Large Telescope in Chile, the 30-meter telescope in Hawaii, the Giant Magellan Telescope in Chile, will have significantly larger collecting areas than Webb and will use different observational techniques, including high-contrast imaging and high-resolution spectroscopy that may allow atmospheric characterization of Earth-like planets around Sun-like stars. These capabilities will be available within the next decade. Space-based missions, specifically designed for exoplanet atmospheric characterization, are under study at multiple space agencies. NASA's Habitable Worlds Observatory concept, a mission designed specifically to image Earth-like planets around Sun-like stars and characterize their atmospheres, is in the early stages of study following its recommendation by the 2021 Decadal Survey for Astronomy and Astrophysics. The European Space Agency's LIFE mission concept similarly targets the direct detection and characterization of potentially habitable exoplanets. These missions, if built, would have the capability to directly detect biosignatures, if they exist, in the atmospheres of potentially habitable planets around nearby Sun-like stars within approximately 15 to 30 light-years of Earth. The result would be a direct observational constraint on the frequency of life in our cosmic neighborhood, either positive detections of biosignatures on some fraction of examined planets, or upper limits on the prevalence of biology at the atmospheric detection threshold. Meanwhile, within the solar system, the missions to Venus under development will constrain the history of Venus's habitability, specifically whether Venus ever had liquid oceans and when it lost them, and whether the loss was gradual or abrupt. The implications for understanding the prevalence of habitable conditions extend well beyond the solar system. Venus is the best studied example of a planet near the inner edge of the habitable zone, and understanding what determined its fate will inform calculations of the habitable zone boundaries for exoplanets around Sun-like stars. The Mars Sample Return mission, the ongoing project to collect samples gathered by the Perseverance rover and return them to Earth for detailed laboratory analysis, will provide the most detailed chemical and mineralogical analysis yet of ancient Martian material. If life existed on early Mars, there is a possibility, though no certainty, that the ancient sediments of Jezero crater preserve some record of it. The laboratory analysis of returned samples would constrain this question far more tightly than any in situ analysis the rovers can perform. The astrobiological implications of Mars sample return go beyond the specific question of Martian life. The detailed chemistry of ancient Martian sediments would constrain the conditions in which the sediments were deposited, the temperature, the pH, the oxidation state, the specific chemical environment of the ancient lake that filled Jezero crater. These constraints would test the models of early Mars's habitability at a level of detail not currently possible. Let us now talk about the specific question of what distinguishes the planets where life develops from those where it does not, about what we do and do not understand about the origin of life, and what this implies for the prevalence of living worlds. The origin of life on Earth, the specific sequence of events and conditions that produce the first self-replicating, metabolically active entities from abiotic chemistry, is one of the most significant open problems in all of science. We know approximately when it happened. The geological record suggests life was present by at least 3.5 billion years ago, and possibly as long as 3.8 to 4 billion years ago, very shortly after conditions on Earth's surface first became stable enough for liquid water to persist. We do not know exactly how it happened. The chemical steps that are required, the formation of nucleotides and amino acids from simple organic precursors, the polymerization of these building blocks into RNA and protein chains, the organization of these polymers into systems capable of self-replication and metabolism, the encapsulation of these systems in membranes that produced the first cell-like entities, are individually studied in laboratory settings and are individually achievable under specific conditions. The specific conditions that enabled all of these steps to occur simultaneously, in a sequence that could lead to self-sustaining life, are debated. What the geological record's early date for the origin of life suggests is that the process was not extraordinarily slow, that once the conditions for liquid water were stable on Earth, life appeared relatively quickly by geological standards. This observation is sometimes interpreted as evidence that the origin of life is relatively likely given the right conditions, that the chemistry is not impossibly rare, that if you provide a world with liquid water and the right chemical ingredients and sufficient time, life is a probable outcome. But there is a selection effect to consider. We observe the origin of life on Earth and we find that it happened early. But this is precisely what we would expect to observe, regardless of how common the origin of life actually is, because we exist, and we exist only on a planet where life originated. If the origin of life were extraordinarily rare, if only 1 in 10,000 habitable planets produced life, we would still find ourselves on one of the planets where it happened, and we would still observe that it happened early and apparently readily. The observation that life appeared quickly on Earth does not, by itself, establish that the origin of life is common. What would actually constrain the probability of life's origin is finding life, or evidence of past life, on a second, independent world. If Mars once had life, independently of Earth, this would establish that life's origin can occur on multiple worlds, given habitable conditions, dramatically increasing our estimate of the probability of life elsewhere. If Mars never had life despite being habitable for hundreds of millions of years, this would constrain the probability of life's origin in the other direction, suggesting that habitable conditions are necessary but not sufficient, that the chemistry of life's origin is perhaps harder than Earth's early occurrence suggests. This is why the Mars Sample Return mission and the search for biosignatures on potentially habitable exoplanets are among the most important scientific investigations of the current era. They are not just questions about specific planets. They are the most direct available tests of whether life is common or rare, of whether the universe is teeming with living worlds, or whether Earth is an exceptional case of life arising in an otherwise largely abiotic cosmos. Let us now talk about what makes this moment in Earth's history specifically significant from the perspective of the larger cosmic story, about why the emergence of a technological civilization capable of understanding its own planetary situation represents a specific kind of threshold in the history of life. For the first 4 billion years of Earth's history, life existed without any component capable of understanding that it existed, or of understanding the planetary context of its existence, or of making choices that could affect the trajectory of the biosphere or the planet. Life happened. Photosynthesis transformed the atmosphere, organisms shaped the climate, evolution generated extraordinary diversity. But all of this happened without intention, without awareness, without the capacity to understand what it was or why it mattered. The emergence of intelligence, and specifically of technological civilization, with the capacity to do science, to understand the physical mechanisms that sustain planetary habitability, to observe other worlds and understand their histories, represents a qualitative change in what life on Earth is capable of. For the first time in Earth's history, a component of the biosphere can understand the planetary context in which it exists, can understand that the conditions sustaining the biosphere are not permanent, can understand the mechanisms by which those conditions could be degraded, can, in principle, take actions that affect those mechanisms. This capacity is not automatically used wisely. The same intelligence that produced the science that allows us to understand planetary habitability loss also produced the industrial economy that is changing the atmospheric chemistry at rates that the geological thermostat cannot compensate. The same civilization that has characterized the mass extinctions of the geological past is producing a new one. Understanding and wisdom are not the same thing, but the capacity exists, and the existence of the capacity is itself historically unprecedented on this planet. The question of whether the capacity is used, whether the specific moment when life first understood its own planetary situation is also the moment when it began to act on that understanding in ways that sustain rather than degrade the conditions for life, is one of the defining questions of the current era. The parallel from planetary science is instructive. Mars did not have the capacity to prevent its own habitability loss.
The cooling of its interior, the death of its magnetic field, the stripping of its atmosphere. These happened because physics demanded it, without any possibility of intervention. The outcome was fixed by conditions set at formation. Earth, uniquely, has produced something that has the capacity to understand what is happening and to act on that understanding. Whether that capacity is sufficient to affect the outcome, whether intelligence can actually make a difference to the trajectory of a planet's biological future, is an empirical question that the current era is in the process of answering. The answer matters not just for Earth. If intelligence can understand its planetary situation and successfully navigate the transition to sustainable practices, if the emergence of technological civilization on a planet turns out to be a resource for that planet's biological future rather than a threat to it, this has implications for the prevalence of life across the galaxy. Civilizations that successfully navigate this transition persist. Those that do not join the list of dead worlds. Whether the specific civilization currently occupying Earth is one that navigates the transition or one that fails to, this is not determined by physics. It is determined by choices. Choices that are being made now, by people alive now, on a timescale that is not geological but historical. Not millions of years, decades. Let us now talk about what the experience of looking at dead worlds teaches, about what it means to understand planetary death from the inside, while still alive, on a world that is not yet dead, but that carries the evidence of how worlds die. The evidence is not abstract. The channels carved by ancient Martian rivers are real features on a real landscape. They are visible in images taken by spacecraft orbiting a world that sits in the same solar system as Earth, 55 million to 400 million kilometers away, depending on where both planets are in their orbits. The minerals deposited in ancient Martian lakes are being sampled by rovers whose instruments we designed, whose data we receive in real time, whose discoveries are published in journals that anyone can read. Venus, shrouded in clouds, its surface hidden from optical telescopes, its hellish conditions destroying every spacecraft that has landed on it within hours, is less directly accessible, but no less real. The Magellan radar maps of its surface show a world of volcanic plains and ancient highlands, and a geological history that is still being reconstructed from incomplete data. The future missions will fill in the picture, and what they will reveal is the history of a world that may have once held oceans, that may have sustained conditions compatible with life for billions of years, and that now maintains surface temperatures hot enough to melt lead under an atmosphere of crushing carbon dioxide. What does it mean to look at these worlds and understand what happened to them? Not as abstract scientific facts, but as realities, as actual worlds that actually exist in actual space, close enough to visit, if not yet close enough to visit easily, whose histories are preserved in the rocks and minerals and atmospheric chemistry that we can study with increasingly capable instruments. It means something that is difficult to name precisely, but that I think is worth trying to name. It means that the conditions for life are not the default state of matter. They are the exception, produced by specific processes, sustained by specific mechanisms, lost through specific failures of those mechanisms. The universe's default is not life. Its default is the vast, cold vacuum between the stars, the cratered, dead surfaces of worlds without atmospheres, the crushing heat and pressure of worlds that ran too hot. Life is what happens when conditions are specifically right for specifically long through specific chains of physics and chemistry that happen not to break. Earth is what happens when all of that works. For 4 billion years, all of it has worked. The magnetic field and the thermostat and the tectonic system and the photosynthetic oxygenation and the evolution of complexity and the entire extraordinary, unbroken chain of conditions and events that led to the current moment. The history of Earth is, among other things, the history of all the ways that this chain could have broken and did not. All the asteroid impacts that could have sterilized the surface and did not. All the volcanic episodes that could have triggered runaway feedback and did not. All the solar flares, all the orbital variations, all the ways the physics could have gone wrong and the chain could have broken, and it did not. It held. For 4 billion years, it held. Mars and Venus remind us that it does not always hold, that there are worlds where the chain broke, maybe at the magnetic field, maybe at the thermostat, maybe at some earlier link we have not yet identified, and where the conditions for life were lost as a consequence. They remind us that the chain holding on Earth is not a given. It is the specific outcome of a specific physical history that happened to work out, surrounded by planets whose physical histories did not work out in the same way. To understand this, to genuinely understand it, not as an abstract fact, but as the reality that it is to understand something about what Earth is and what the life on it represents. Not sacred, not cosmically special in any metaphysical sense, but specifically precious in the physical sense of being rare and contingent and the product of conditions that are not guaranteed. And to understand this is to understand why the question of what happens to those conditions, in the long term through planetary physics, and in the near term through the choices being made by the one species capable of affecting those choices, is among the most important questions that have ever been asked. The universe has given Earth an extraordinary run. 4 billion years, complex life, intelligence, the capacity to understand all of this, the capacity to act on that understanding. What happens next is not determined by physics. Go outside tonight and look up. Find Mars, if it is visible, a reddish point of light, steady against the background of stars, moving slowly against them from night to night. It is between 55 and 400 million kilometers away, depending on where both planets sit in their orbits. Close enough in cosmic terms to visit, close enough to study in detail, close enough to read its history in the rocks and minerals that rovers have been sampling for 2 decades. That point of light was once something different. 3.5 billion years ago, Mars had rivers. Not metaphorical rivers, actual rivers carved into actual rock in drainage patterns that branched and merged in the specific geometry that moving water produces when it flows across a landscape over long periods. It had lakes. Jezero Crater, where the Perseverance rover is driving across an ancient delta right now, collecting samples that may one day return to Earth, was a lake. Water flowed into it through a river. Sediments accumulated on its floor. The chemistry was warm and wet, and by every indication we have, compatible with life. And then, gradually, over hundreds of millions of years, it ended. The magnetic field died. The interior cooled. The convection that generated the field slowed and stopped. And the solar wind had direct access to the atmosphere. The solar wind stripped it, 100 grams per second, every second, for billions of years. The lakes dried. The rivers stopped flowing. The surface froze. The ancient river valleys are still there, preserved in the cold and the dryness, visible from orbit, visited by rovers. But the rivers that carved them have been gone for longer than complex life has existed on Earth. Mars is what happens when the chain breaks. Now find Venus in the sky, the brightest point of light other than the moon, brilliant white, visible in the west after sunset or the east before sunrise. Almost exactly Earth's size, almost exactly Earth's mass, orbiting the same star in the same solar system, formed from the same primordial material. Its surface temperature is 465 degrees Celsius. Its atmospheric pressure is 92 times Earth's. Every spacecraft that has landed on it has been destroyed within 2 hours by the heat and the crushing pressure. The clouds that make it so brilliant from Earth are made of sulfuric acid. The best current models suggest it may have had liquid oceans for 2 to 3 billion years, longer than multicellular life has existed on Earth. Long enough, possibly, for life to have begun, for chemistry to have organized into something self-replicating and metabolic, for evolution to have started its slow work. We do not know whether it did. We do not know whether the ancient highlands preserved under the clouds hold any record of what Venus once was. The missions currently being built will begin to answer these questions within the next decade. What we know is that whatever Venus once was, it is not that now. Something changed. The solar luminosity brightened slowly, or the volcanic activity shifted, or some threshold was crossed that set off a feedback that could not be stopped. And Venus transitioned from a world that may have been habitable to a world that is definitively not. And it has stayed there for hundreds of millions of years, possibly longer. The transition, once made, held. Mars and Venus are the two most Earth-like planets in the solar system. Both appear to have lost, or severely degraded, the conditions for life through mechanisms that are now well understood. The mechanisms are not exotic. They are the normal physics of planetary evolution: internal cooling, atmospheric loss, climate feedback, playing out on timescales that are long by human standards and brief by cosmic ones. Earth sits between them, literally in orbital terms, between the orbit of Venus and the orbit of Mars. And in the space of planetary possibilities, Earth sits in a range of conditions that both of its neighbours appear to have exited. How long has Earth been in that range? Approximately 4 billion years. How long will it remain? On the longest timescale, before the brightening sun eventually triggers the kind of feedback that may have transformed Venus, perhaps 1 to 1.5 billion more years. Before CO2 concentrations fall too low to support plant photosynthesis, perhaps 600 million years. Before the biosphere, in its current complex configuration, can be said to be secure from the specific pressures of the current era, that is, measured not in millions of years, but in decades and centuries. These are very different timescales, and they demand very different things. The billion-year timescale is not a human problem. The planetary physics that will eventually end Earth's habitability is not something any civilization can address with current or foreseeable technology. It is the eventual fate of the planet, fixed by the same physics
that determined the fates of Mars and Venus. We understand it, which is remarkable. We cannot change it, which is humbling. The million-year timescale is also not a human problem in any direct sense. The gradual changes in CO2 concentration driven by the carbonate silicate thermostat, the slow brightening of the sun, the eventual cooling of Earth's interior, these are geological processes operating on timescales that dwarf the entire history of human civilization. But the decade to century timescale is precisely a human problem. The specific changes currently underway in atmospheric chemistry, in ecosystem integrity, in the distribution and abundance of species across the planet are happening on timescales that are measured in human lifetimes. The choices that determine whether those changes stabilize or continue are being made now, by people alive now, in political and economic and technological decisions that have specific and measurable consequences on timescales that are not geological but immediate. This is what the comparison with Mars and Venus ultimately reveals. Not that Earth is doomed, it is not, at least not on any timescale that matters to us. Not that catastrophe is certain, it is not, and the framing of inevitability serves no one. But that the conditions sustaining Earth's extraordinary biological complexity are not guaranteed. They were not guaranteed when Mars lost its magnetic field. They were not guaranteed when Venus lost its oceans. They are not guaranteed now. They are sustained by specific mechanisms, the thermostat, the magnetic field, the tectonic system, that have worked for 4 billion years and will continue working for millions more. And they are sustained by the integrity of the biosphere, the specific living system that participates in the regulation of those mechanisms, that has transformed the atmosphere and shaped the climate, and made the planet more habitable for complex life over billions of years. Disrupting that living system, rapidly, at scales that exceed the capacity of the thermostat and the ecosystem to compensate, does not trigger a Venusian runaway. The physics of that transition are more severe than anything current trajectories approach. But it does degrade the specific configuration of the biosphere that sustains the ecosystem services civilization depends on. It does reduce the resilience of the system to other perturbations. It does eliminate species that cannot be recovered on any timescale relevant to human civilization. In short, it makes the window smaller. Not dramatically, not catastrophically, not on the scale of planetary death, but measurably in ways that matter in the specific time frame that matters for us. Mars's ancient river valleys are one of the most moving things in the solar system, not because they are beautiful, though images of them are striking, but because of what they represent. A world that had water, that had rivers, that may have had the beginnings of chemistry organizing toward life, that lost all of it through mechanisms that no part of that world could understand or resist. No intelligence looked at the Martian sky 3.5 billion years ago and understood what was happening. No awareness watched the atmosphere thin and the lakes dry and the rivers slow and stop. It just happened because physics demanded it, without witness, without understanding, without any possibility of response. Earth has something Mars did not. Earth has a component of its biosphere that can understand what is happening, that can look at Mars and Venus and read what they reveal about how habitable worlds end. That can measure the atmospheric chemistry and the species loss and the ecosystem degradation and understand what they mean. That can, in principle, make choices that affect the trajectory. Whether that capacity is sufficient, whether intelligence actually helps a planet maintain its habitable conditions, or whether it tends to degrade them, is an empirical question that the current era is answering. The universe may be full of dead worlds, worlds that began with rivers and lakes and warm chemistry and the potential for life, and that lost it through the normal physics of planetary evolution. Worlds that were briefly alive, or almost alive, and are now frozen or burned or stripped bare. Worlds that went through the extraordinary 4 billion year chain of maintained conditions and lost it at some link in the chain. Worlds that generated life and then lost the conditions that life required. Earth may be next, in the long view. It certainly will be, eventually. The physics demands it. But not yet. Right now, Earth has what Mars lost 3.5 billion years ago, and Venus may have lost 700 million years ago. Liquid water, a functioning atmosphere, a magnetic field deflecting the solar wind, a tectonic system recycling carbon, and something neither of those worlds apparently ever had, a species capable of understanding all of this. That is not nothing. That is, by the evidence of the solar system, extraordinarily rare. The question of what we do with it is not a physics question. It is the only question that has ever really mattered.